Question 20. A body of mass 0.5 kilogram. Mass is given 0.5 kilogram. Then travels in a straight line with the velocity v is equal to a x raised to 3 by 2. You have to see here that formula carefully. A is not acceleration, a is a constant only. And x raised to 3 by 2 means it says that velocity depends on position x. That's the meaning. Where a is equal to 5 meter raised to minus 1 by 2, second raised to minus 1. That's the value of a. Then that's the value of a, and a is constant. Okay, not the acceleration. Please understand. Then what is the work done by net force? What is the work done by net force during the displacement from x equal to 0 to x equal to 2 meter? Okay, so value of a is given. A is equal to 5 meter raised to minus 1 by 2. It's a constant with the unit. Okay, and second raised to minus 1. Then initial position xi equal to 0 and final position xf is equal to 2 meter. So here we can calculate kinetic energy. We calculate kinetic energy, just calculate initial kinetic energy. Ki is equal to half m v square. Initial kinetic energy we can take u, half m u square is equal to half m into the value of v we can substitute there. Then it becomes a square into, you see initial position is 0, xi is 0. So initial position is 0. So it becomes 0 square. So what is the initial kinetic energy then? Initial kinetic energy is 0. And if you substitute here value of x, okay, 0 raised to 3 by 2 is value of x as 2, you will get a final kinetic energy. Now what you have to do to get the work? The work done is equal to, again we apply work energy theorem. Okay, Ki minus Kf, or we can take delta K. Their initial kinetic energy is 0. As initial kinetic energy is 0, just we can consider as work done. Only magnitude we will take, no need to take negative sign and all, we will take a half m v square. Remember, this is final kinetic energy only. Now substitute the values, half into value of m is 0.5 into velocity is a x raised to 3 by 2 the whole square. Okay, value of x you have to substitute as xf is equal to 2 meter, you have to substitute there. So you will get the change in kinetic energy, and change in kinetic energy will be work done here. Okay, so use the work energy theorem, use the idea work done is equal to change in kinetic energy. Initial kinetic energy is 0, so you need to calculate only final kinetic energy, and final kinetic energy W is equal to half of v square. Value of v is equal to ax raised to 3 by 2, and where x is equal to 2 meter, the value of final position you need to substitute there, you will get the answer. Now, next question 21. The blades of a windmill sweep out a circle of area A. Area is given A. Then part A of the question. If the wind flows at a velocity V, velocity of the wind, perpendicular to the circle, means the perpendicular to the blades. What is the mass of the air passing through it in time t? That is part A. Mass of air passing through it. Okay, so first of all, here, one of the previous chapters, I told the meaning of velocity into area. Velocity into area, when we use their corresponding units, you will get a meter per second into meter square. That means you will get a meter cube per second. So meter cube per second means it is volume per second. Therefore, by multiplying velocity and area, you will get a volume per second is equal to area into velocity, volume per second. And if you get volume per second, now you can calculate mass per second. Mass per second is equal to, how can you calculate mass per second? Volume, when you multiply by density, you will get a mass. So volume per second, when you multiply by density rho, you will get mass per second. So you know mass per second, then how can you calculate the mass? In 1 second, AV rho. In t seconds, you will get AV rho into, that is the first answer, AV rho. Answer to case A. Now, next case B. What is the kinetic energy of the air? So, how can you find kinetic energy of the air? B is equal to, kinetic energy is equal to, half mv square is equal to half into m. We have calculated already. Value of m is A B rho t into v square is equal to half A v cube rho t is the kinetic energy. So that is answer to part B. Then assume that the windmill converts 25% of wind's energy into electrical energy. Area, velocity, density, all quantities are given. What is the electric power produced? First of all, you can calculate power produced. So can you calculate power produced? So answer to part C, power produced, P is equal to energy by time. Here energy means kinetic energy. So you will get the answer half A V cube rho. T will be cancelled. Now this power is converted to electric power, but we know that only 25% is converted to electric power. Therefore, how much is the electric power produced? The electric power produced, P is equal to 25% of power of the wind. So first you calculate half A V cube rho. Its 25% is converted to electric power. So you will get the answer, the electric power produced. So that's about a question 21. Next, question 22. A dieter Okay, lifts 10 kilogram mass 1000 times to a height 0.5 meter. Means you can calculate potential energy there, mgh. 1000 times. So how much energy the dieter spends as the potential energy? That is what we are calculating now. I think you will get the answer around 50,000. 50,000 joule. Now, that is a potential energy. That much of energy is spent by the dieter to give the potential energy of the object when it is lit. Then, uh, how much work does she do against gravitational force? That is what this 50,000, okay, joule. Then next part B. So this is the answer to part A. Okay. Now part B. Part supplies 3.8 into 10 power 7 joule of energy per kilogram. Per kilogram. That means 1 kilogram of fat gives 3.8 into 10 power 7 joule. Then how much amount of fat is required to have 50,000 joule of energy? So mass of fat you have to calculate. Mass of fat is equal to total energy obtained from the fat is 50,000 joule divided by 50,000 joule divided by 3.8 into 10 power 7 joule per kilogram. So that will give the mass of fat. But at the same time, you see the question, the efficiency rate is 20%. What does it mean? If 100 kilogram fat is converted into energy, then you will get only 20 kilogram directly converted into energy. The rest is lost. That means whatever quantity here you got is the MF is the 20% of actual fat is melted. Okay, once again I repeat, as the efficiency is only 20%. Whatever mass we got, which is exactly totally converted into energy, is only the 20% of actual fat. Therefore, the mass of actual fat, MF, okay, and it's 20% only exactly converted to energy, small MF we can take, which we have calculated here in this case. Therefore, what is the actual mass of fat lost? MF is equal to 100 MF divided by 20 will give you the final answer. So that's about question 22. Come to question 23. A family uses 8 kilowatt power. The total required power is 8. 8 kilowatt means it is 8 into 10 power 3 watts. That much power is required. Direct solar energy is incident on a horizontal surface at an average rate of 200 watts per square meter. That means you are getting solar energy with 200 watts per square meter. And it's 20% of this energy can be converted into electrical energy. That means what is the power obtained per square meter? We are getting 200 watts, but power per square meter, power per square meter will be 20% of 200. 20% of 200. So you will get 40 watts. That means you can convert only 40 watts of solar energy, 40 watts of solar energy per square meter. And you need how much power? 800 kilowatt power. 800 kilowatt. So 40 watts per meter square we will get. So how much will be the area then? So area of solar panel is equal to 8 into 10 power 3 watts divided by 40 watts per square meter. Okay. Per square meter. So watts will be cancelled. So you will get the answer around 200 meter square. 200 meter square is the answer. Next, question 24. A bullet of mass 0.012 kilogram. Mass of the bullet. Okay. Mass of the bullet we can take as small m. Small m is equal to 0.012 kilogram. With a horizontal speed of 70 meter per second. That is initial speed. We can take the speed of initial speed of the bullet 70 meter per second. Strikes a block of wood of mass 0.4 kilogram. Let it be big M is equal to 0.4 kilogram. And instantly comes to rest with respect to the block. That means the bullet gets embedded inside the block. The block is suspended from the ceiling. The block is suspended from the ceiling by means of thin wires. Okay. Calculate the height to which the block rises. So here the block is suspended like this. When the bullet hits, you can see the block goes upward. And how much is the height to which the block is lifted? Also estimate the heat produced. So these are the concepts given. So first of all, it is something like collision, so we can apply law of conservation of momentum. By applying law of conservation of momentum, we have an initial momentum m into ub is equal to final momentum capital M plus small m into v, where v is the initial velocity of the block with which it rises. So from this equation, rearrange this equation and find the initial velocity of the block. You can find the initial velocity of the block. Then use the formula use the formula V square is equal to V square is equal to U square plus 2AS. So here you can see when the block rises, its final velocity will be 0 and its initial velocity will be this capital V which we have calculated minus 2GH. From this equation, you can find the value of H. H is equal to V square divided by 2G. So you can find the value of H. Now next, also estimate the amount of heat produced in the block. So how can you estimate the amount of heat produced in the block? You know, heat produced will be the loss of energy. So heat is equal to, we can take the total initial energy is equal to half m UB square, the kinetic energy of the bullet. And final energy will be the kinetic energy with which the block and the bullet begin to rise. That means half into that. Here m plus m into v square. So this is the second term represents the kinetic energy acquired by the block when bullet is inside. The difference in energy is converted into heat energy. That much energy is lost in the form of heat during the collision. Okay, so try to find the answer. Now next question 25 has been discussed already. 26 also. Now come to question 27. Question 27. A bolt of mass 0.3 kilogram, mass is given, falls from a height of the ceiling of an elevator moving down with a uniform speed. It hits the floor of the elevator. Okay, length of the elevator is 3 meters. That means the height is 3 meters and does not rebound. Okay, what is the heat produced? That means does not rebound means whatever potential energy it was in the beginning is now converted into kinetic energy and which is again converted into heat energy. The whole energy is lost in the form of heat. That is why it does not rebound. Therefore, how much heat energy is produced? We can say heat energy H is equal to mgh. Again, I repeat, first at the height h, that is 3 meters, it has potential energy. Potential energy is converted into kinetic energy, and when it hits the floor, the whole kinetic energy is converted into heat energy. So you can find the answer. Then would your answer be different if the elevator were stationary? Whatever it is stationary or moving, okay, its potential energy is converted into kinetic energy. So answer will be same only. Potential energy is converted into kinetic energy, then it is converted into heat energy. That's all question 27. Now come to question 28. Can you see question 28? Okay, trolley of mass 200 kilogram moves with a speed 36 km per hour, convert into meter per second on a frictionless track. A child of mass 20 kg on the trolley from one end, the child is at one end of the trolley, and trolley has a length of 10 meter, and the child has a speed of 4 meter per second relative to the trolley in a direction opposite to its motion. That you have to note very carefully. Okay, this is relative velocity. 4 meter per second relative to trolley means velocity of the child with respect to trolley in the opposite direction and jumps out from the trolley. What is the final speed of the trolley and how much has the trolley moved from the time the child begins to run? So that's the question. Okay, so first we will start from here, that relative velocity. Relative velocity of the child with respect to trolley is equal to Vc plus Vt. You know why I have taken Vc plus Vt? Because velocity of the child and velocity of the trolley are in opposite direction. From there, you can calculate the velocity, and this value is given in the question. It is 4 meter per second. From there, the velocity of the child, you can calculate, it is 4 minus Vt. 4 minus Vc is equal to 4 minus Vt. Now, initially, the child is in the trolley. So, initial momentum Pi we can calculate. Initial momentum Pi is equal to mass of the trolley plus mass of the child. And the trolley is moving with a velocity 36 km per hour. That 36 km per hour I'm going to take as ut. Okay, so here ut is equal to 10 meter per second. That means 36 km per hour. That is the initial moment. Now, final moment. How much is the final momentum? The final momentum we can take as minus mcvc, that is momentum of the child plus momentum of the trolley, mt vt. What is this vt? Vt is the velocity acquired by the trolley when the child starts running. Okay, that final speed. And here again we put a negative sign because now the momentum of the trolley and momentum of the child are in the opposite direction. And again the child is sitting in the trolley and the child gets up, then runs. So there is no effect from outside. Therefore, no external force. The law of conservation of momentum we can apply. So you will get mt plus mc into ut is equal to minus mcvc plus mtv. Now look at the equation. All quantities are there. Here you don't know the value of vc. So what you have to do? You have to take this is equal to minus mc, then vc is equal to 4 minus that velocity ut you have to take. Sorry, 4 minus vt. 4 minus vt plus mtvt. We now simplify the equation and find the value of Vt. You will get the value of Vt approximately 10.36 meter per second is the value of Vt. Just to substitute here in this formula and verify whether you are getting the answer or not. Now, so this is the velocity of the trolley. Now, we can calculate time taken by the child to complete the motion. Time taken by the child is, we can take distance divided by time, sorry, distance divided by speed is equal to distance traveled by the child is 10 meter with a relative velocity 4 meter per second. So child takes around 2.5 seconds to complete the motion over the trolley. Why then? What is the distance traveled by the trolley? That is the second part of the question. What is the distance traveled by the trolley? Okay. Once the child starts motion, this is the velocity of the trolley. Therefore, distance traveled by the trolley will be distance of the trolley dt is equal to vt into t. Okay, so what is the distance traveled by the trolley after the child begins running? So child runs for a time 2.5 seconds. By then the trolley moves with a velocity of 10.36 meter per second. Therefore, distance traveled by the trolley is equal to 10.36 into 2.5. So you will get the answer, the distance traveled by the trolley. Then next question 29. Which of the following potential energy curves cannot possibly describe the elastic collision of two billiard balls? One of the previous problems we have seen. The potential energy, if it is elastic collision, then potential energy is the function of distance. We have seen potential energy is the function of distance. So here we can take that concept. So what kind of relation between potential energy and distance? When the distance increases, the potential energy decreases. So a collision you can take when the objects they are coming close to each other due to some attraction like that you can take, then you can see what happens there. In such a situation, the potential energy decreases and kinetic energy increases. So you have to take the derivation and all we will do in another chapter, gravitational force. So the potential energy distance relation is actually an inverse relation. Potential energy V proportional to or P proportional to one by R. P proportional to 1 by R. Now look at these graphs. Reciprocal graph, you know, the shape of reciprocal graph will be like this. So P and R. We have only one graph in that way. Okay, this graph. So that graph 5 represents elastic collision. And all other graphs cannot represent elastic collision because that inverse relation you cannot see in any of the graphs. Okay. Therefore, graph 5 represents potential energy, the relation between potential energy and distance. Relation between potential energy and distance. Okay, so here you have to take the billiard balls. So this kind of a situation you can see. And what happens during the collision in one of the previous problems I mentioned. So here the shape of the ball changes. Now the distance is r plus r 2r. At that moment there is no potential energy. Then afterwards what happens? The balls get deformed like this. That means the distance between them is less than 2r. That time what happens? Their kinetic energy is momentarily converted to potential energy. Kinetic energy is momentarily converted to potential energy. So that is why here you can see in this graph, when the distance is less than 2r, potential energy increases. And when the distance is 0, that means that these 2 points, 2 centers will coincide. The potential energy is maximum. So potential energy is maximum when these 2 centers coincide. Then up to 2r in this situation, there is no deformation. Potential energy is 0. Okay, that means when the distance from the centers or distance between the centers increases, potential energy decreases. When the distance increases, potential energy decreases. That is the reason I told in the beginning, potential energy and distance are inversely proportional. That condition is satisfied only in this graph. Okay. Therefore, graph 5 represents elastic collision, because for elastic collision, the potential energy depends on separation distance, according to which we have discussed in question 8, part D. Therefore, only that graph represents elastic collision. All other graphs cannot represent elastic collision. I think that is enough. Okay, so thank you.